Hello and welcome to this session on statistical analysis. In Module 1 I covered the basic statistics and some quality tools. In this module we'll follow that with a discussion of control chart, process capability, and cover Six Sigma, and essentially covers the three chapters of the text, chapter 11, 12, and 13 in this module. So control charts. In module 1 I talked about run chart. Run chart is a plot of any measure of interest, output, performance over time. And control chart is nothing more than a run chart, except that it has control limits. So if you see here this plot of the measure is similar to what we did for the run chart, but in this case now I have the upper and lower control limit. The idea here is that any process, there is always an inherent variability in any process, and we'll show that by how that variation shows around the mean of the process. Now in control chart, when we set the control limits, that is based on what Schuhart invented. The control chart was based on the idea that the three sigma, three standard deviation up and three standard deviation down, which covers 99.7% of the all observation, is the good way of understanding whether or not the process is in control. Now, the idea the process is a control means that the variation is randomly distributed around the mean, and it is within this three standard deviation. So, just like this point, when it's outside the control limits, higher than the upper control limits, then we say this process is out of control. And the idea is that something else has happened to the process. This variation is not due to its internal variation of the process, but some external factors has impacted the process, and so it went out of control. So then the notion is that once you observe an output of this sort being out of control, then you need to investigate to find out what caused that problem, and then if you remove the cause of the problem, hopefully the process gets back into being under control. So here's an example of control chart where we have here's a process when you plot the observations over time, and you have the control limits, upper control limit, lower control limit, and as I showed before, here's a data point that's outside the control limit, so we call that out of control, and we have to find out what has caused that. Once you identify that, then and remove it, the process gets back into a control process, and you can see this variation randomly above and below the mean. Now this latter part shows that if we make actual improvement to the process to reduce its variation and then recalculate the control limits, you will see that the data points are closer to the mean. In this case variation is less, and so the control limits are much narrower than it was in this process. Now there are many different types of control chart used for different purposes, and in the text shows a flow chart that under various conditions, you choose one type of control chart over another control chart. But in this presentation, I'll talk about a few more commonly used control chart, particularly as I showed before. If the process is normal, the control limits are essentially 3 times of the standard deviation. So you calculate your mean, you calculate your standard deviation, and then plot the upper and lower control limit as 3 times standard deviation plus mean, and 3 times standard deviation subtracted from the mean as lower control limit. But not all processes are normal. So if the process is not normal, or we are not sure about it, you plot the histogram and you don't see that's closely following a normal curve. Then the idea is that, well, what do we do now? So X bar and R charts are substitute for processes that are not considered to be normal, and a combination of these two will show whether or not the process is in control. Now, the concept behind the X bar and R chart is that if you have a set of data that you consider not being normally distributed, if you divide that data set into segments of 5 or more data points into groups of the same size, the mean of those groups and the range of those groups are always normally distributed. So we can apply the concept of the control limits based on that 3 standard deviation to the mean and the range of the process, and then look at it and see whether or not the process is in control or not. So let me illustrate that with an example here. So let's say that in the following data we're tracking production hours for a particular machine, and so here's the week 1, 2, 3, 4 up to 10 weeks, and Monday, Tuesday, Wednesday, and Thursday, and Friday. So I've got 5 data points in each of these groups. In other words, if you would have looked at all the data together, you go from here, all the way to the end of the 10th week. So with 50 data points. But if we look at them as groups of 5, so I'm looking at these on a weekly basis, then I can calculate the mean of each group. And so if you take the group 1, we've got 4, 3, 4, 4, 5, and you add them up and divide them by 5, and you get 4 as being the mean. And then I need to also calculate the range of the group. Now, the range is the difference between the largest and the smallest value. So here's 5 minus 3, the range is 2. I go to the second group. Here we've got 3, 3, 3, 3, 4. You calculate the means 3.2, and the range is 4 minus 3 is 1, and so forth. So I've got these two columns. One column is represent the mean of the group, and the other one represent the range of the group. Now, as I said before, statisticians have shown that the distribution of X bar and the distribution of R are always normally distributed. So based on that, then they have given us formulas to calculate the upper and lower control limits of these groups, and then we'll look at that and try to refer to the underlying process whether or not that is in control. So in that example, I had 10 groups, and there are 5 observations in each group. Calculated the X bar for the subgroups, and calculated the R for each of the subgroups, and then calculated the mean of the range. In this point, the sum of that column is 17, divided by 10 is 1.7. And we also calculated the mean of the means. So this I'll show that with the X double bar means that it is the mean of each group. And so that's an average of the X bar. So to get the control limits for the R chart, the formula is upper control limit is D4 times the average of range, and lower control limit is D3 times the average of range. Now, where did the D4 and D3 comes? This has been calculated by the statistician, and they're always available in tables in any statistic books on statistical process control. So the way the table is set up is that based on how many items or how many data points is in each group, then you know what the value of A, D3, and D4 are. So in this case, we have 5 items in each group. So if you look at the 5, then the value of D3 is 0, and the value of D4 is 2.11. So if you substitute 2.11 multiplied by 1.7, which was the average of range, that gives us the upper control limit for the R chart as 3.6, and since D3 is 0, the lower control limit is 0. The X bar chart, which represents the variation of the mean, the upper control limit is X double bar plus A2 times average of the range, R bar, and the lower control limit is X double bar minus A2 times R. So you could see the resemblance to the mean plus and minus to your standard deviation, and this is how it has been calculated. So in this case, x double bar is 3.7, and the A2 from this table for 5 items in a group is 0.58 times 1.7 gives 4.7. X double bar minus the same amount is the 2.7. So now I've got the upper control limits for R chart and lower control limits for both R chart and the X bar chart, and so I can now plot my control chart. So the R chart here, I had the upper control limit 3.6, lower control limit 0, and what you plot is actually the ranges that we calculated, right, from the group. So these points represent the items in that last column of the chart that I showed before. And then you can look at this and say, well, all these data points are within the control limits, so the process is controlled, but then you could have some issues whether or not actually the process is stable or this variation is random. We also plot the X bar chart, and here again we had the upper control limit and lower control limit calculated, and then we plot the mean value of each of the group here as the data points. And you can see that there are a couple of data points that are touching the control limits, and maybe those are the issues that you need to investigate. The others seems to be okay. So by looking at these two charts together, you can infer whether or not the underlying process is in control or not. So that was the X and R bar charts that we're using when the data is not normally distributed, and we're trying to apply the control chart to the variable. Now there's another commonly used chart called INMR chart. And this is INMR chart is actually the same as the X and X bar and R chart, except that in this case the size of the group is 1. Remember, in the previous chart we used a size of 5, and you could have 4, 7, 8, 10. Now if you use the size of 1, then we're getting an I and the moving range chart, which again, similar to that previously, we're going to need to calculate some values for the control limits of the I and the control limits of the moving range. And so for the R chart, the individual x's, which is the individual values, you get the mean value of that, and then plus E2 times MR. Again, this is a factor calculated and is available in any SPC books, and I've showed it here at the bottom. Here is that this is always going to be 2.66 for the IMR chart. So you multiply that, and then here again we have the average of the data points minus the same amount for the lower control limit. But for the moving range, then we have to, and I'm going to show you with examples, the difference between each of the two data points to get the range of the two data points, and then calculate the average of that, very similar to what I did for the R chart. And then here again you could see the D4 for the upper control limit times that average of range, moving range, and the D3 times average of moving range. So in this case, because the number of items in the each group is 1, so D3 is 0 and D4 is 3.267. So now let's look at an example here. So let's say that if you have a number of observations in this column, we've got a 10, 9, 12 all the way, and I'm calculating the mean of that, our variance, the standard deviation. And so this is the, the mean column. And for the R chart, so I use the mean value, which is 9.84, in the mean column, and the upper control limit then is X bar, which is 9.84, plus E2 times MR bar, which is the average of the moving range. Now, how do I calculate the moving range? You look at this column. The moving range is the difference between the two consecutive items. So the first one was 10, the second one is 9, the difference between the two is 1. For the second one, I've got 9 and 12, so the difference is 3. For the third data point is 12 minus 14, it's 2, and so forth. So you get the ranges as each item minus the second item. And we use absolute value, so we don't do positive and negative in this case. So now I've got the ranges here. And if I get the average of that is 4.48, and that's what I'm going to use in here to calculate my upper control limits for the I, and the same thing for the lower control limit. And when I'm calculating the MR chart, the upper control limit is D4 times the average of moving range, which is 4.48. And so if you use the D4 from the previous chart, multiply by that, you get 14.64, and D3 was 0, so this is 0. So you could see here the E2 was 2.66, and D4 is 3.26. That's substituted in there. So with those values now we can plot our values here. It's going to go into the control chart, and the moving range values goes into the control chart. So the R chart here is that these are the actual data points are plotted around the mean value with the upper control limit and lower control limit. And for the moving range, again, the moving range are plotted this way. The mean value, upper control limit, lower control limit. Again, you have to look at these two charts together and make an observation whether or not the process is in control. Certainly we've got a point here that seems to be outside the control chart of both of these almost. And so since the R chart represents the variation of the mean, and the moving range chart shows the representation of the variation, so based on that you could see whether or not where the problem might be in terms of the issues with this process. So that's how you plot the control limit and control chart for X and R bar, R chart, as well as the I and MR chart when we have the data of this sort. So now that's the control chart for variables. Now I'm going to move into another area which we're covering this week, and that is process capability. Now the process capability is the ratio, then kind of be careful in terms of what I'm saying here, is the ratio of the specification spread over the natural tolerance of the process. So when we're plotting control chart, we are essentially plotting the variation of the process. When you put your requirements on that process of what is good and what is not good, then you know whether or not your process is capable to produce good output. And that is shown in here. We're saying the process capability index is the upper specification limit minus lower specification limit, and that shows the tolerance that your design or your customer can accept. That's the has nothing to do with the process itself. That's what you have to produce good product to that specification. Now, if the process has some inherent variation, if we divide that by 6 standard deviation, 3 standard deviation to the right, 3 standard deviation to the left. So if the specification limit over the 6 standard deviation is greater than 1, it means that your tolerance is larger than the variation of the process, so you're getting good output. If the ratio is less than 1, you know that there are variation outside that limit, and I'm going to show that pictorially, and so your process is not capable. In practice, a good process is represented by when the specification limit or the specification tolerance over the 6 standard deviation is greater than 1.25. We call that to be a capable process. And so let me show that pictorially. So we've got a process here, like any process, you plot the histogram and fit the data to that. So I've got a process that has this variation. There's some a lot of output in the middle, and there are some toward the tail of this process. Now, 6 standard deviation around the mean. Here what I'm showing is the 6 standard deviation around the mean. If the specification limit is on the upper limit is over here and lower limit is here, you could see that this distance between the specification limit, that's the tolerance of acceptable output for the design or for the customer requirement. If that's outside the 6th standard deviation, you know whatever the process is producing is good because it is acceptable. If, on the other hand, in here we're showing that the 6th standard deviation goes all the way to here, but your requirement is much tighter. So it means that there are output that falls over here, and there are output that are going to be falling in that range, and they're not going to be acceptable. So you're producing unacceptable product on these ends. So we call that process not to be capable or not capable enough. So when we look at that index, it can tell us whether or not the process can produce good output. We want the process to look like this with respect to our tolerance. And if that's the case, then you're producing less defect or no defect at all when you get to the Six Sigma. But if the process is more like this, has larger variation that your customer can accept or your design can accept. So when we talk about specification limit, there are really two things. So if you're designing products, sometimes that tolerance has to be tight in order for the physics of the problem to work. And so if the tolerance is such tight in here, but the way you're producing the component or the sub products has a much larger variation in the output, the voltage or the tolerance of mechanical parts and so forth, then you're going to have cases where whatever you produce is not acceptable or it's not going to work. Similarly, it could be in other areas, could be customer requirements. You're producing software, the customer may not accept more than so many false pairs, millions of lines of code or 1,000 lines of code. Well, if your process, is much wider in variation and you have more inherent defects in your software, then that's not going to be acceptable. And so we're looking for processes that are looking more like this, and as a result being able to produce a good product, or otherwise you have to go either to rework the output or scrap it and start over again. So what I showed as a CP, the capability index, is that if your process is centered around the specification limit, in other words, the mean of the process and the mean of your specification limits on each other, then the formula I showed before is what you use. You take the difference between the upper and lower specification limit, divide by 6, and that 6 is standard deviation, and give you the capability index. But there are possibilities that your tolerance may not be symmetrical. In other words, you could have an acceptable tolerance of plus 2 volts and minus 0.5 volts. So as opposed to being plus and minus 2, there are upper and lower are different values. Then in that case, we're looking at really whether or not the upper specification limit minus mean value divided by 3. Now you could see that I'm dividing it into half. I'm looking at the right hand side and I'm looking at the left hand side. If you look at this picture here, I have the upper specification limit as being 24, whatever the value was. The mean value is 22. The upper specification acceptable value is 24. The lower specification limit is 18. If the process mean is 22 and the standard deviation is 0.8, you could see that on this end I'm going to have areas where the output is unacceptable. But on this end, because the tolerance is outside the process limit, then I'm producing good output. I have less worry about this. So to get the index, the CPK, we're looking at the minimum value. In other words, where do I have problem? If you take it upper specification limit minus mean, that's going to be 24 minus 22 divided by 3 standard deviation is 2.4. We'll look at that separately, and also we'll look at this other part, which is the mean minus lower specification limit divided by 3 standard deviation. And so you get two different values, 0.83 on the upper side, 1.67 on the lower side. Well, we know the lower side is very good, but the upper side is where I'm going to have a problem. And so my capability is based on the minimum value. So in this case, we say the CPK is 83 would potentially we're going to have some output unacceptable. If on the other hand, in this case, the mean was right in the middle of the specification range, then the CP and CPK would have been the same and come out to 1.25, which would have been a good process. So that covers the specification, the process capability, and we'll have examples and exercise on process capability. And again, let me emphasize that in process capability, you're looking at two different things. You're looking at the process variation, which we're using 3 sigma or 6 sigma, and then overlay on that what is our specification limit, which has nothing to do with the process, but it's a requirement of the product or the requirement of the customer, and then we'll see whether or not the process is capable to produce the good output all the time or some of the time. So now let me move on. We covered the control chart for variables. In chapter 12, we talk about control charts for attributes. The attribute charts are used when we measure defects per unit. So in the variable, we have the continuous variable, and we will measure the values of it over time. But in the attribute chart, we have individual products or that's coming up the line, and there are two ways to check them for quality. You either count the number of defects on a unit that comes out of the production, or you just look at the unit, and if there is any defect on it, you call it defective. So we have two ways of measuring attributes. If you're counting the defects, then a unit may have multiple defects, and we count how many defects are in the unit. If you're counting defective units, then whether or not the unit has one defect or many defects, we'll just count them as defective. So to put control charts for this output, the products coming off the production line or how we're producing them, and see whether or not they're good or acceptable, we have P chart, and P chart are used when we are counting the number of defective units. So in the P chart, again, just very similar to when we talk about the variable chart, we've got a mean value in terms of how many of the, if we're doing sampling, how many of the units were defective as a percentage, plus and minus what is it, is 3 standard deviation of that defective ratio, which is P times 1 minus P divided by number of units in the sample. If the sample size is the same, not or each time we picking up, let's say, a number of units and checking them out, see how many of them good, how many of them bad. If each time we use the same number of units, where then we could use the NP chart, which is very, essentially the same formula that we have for P chart, except that you can see that we have multiplied everything by the size of the unit in the sample. So it's, n shows up in here, and the standard deviation here, you could see that the n has been multiplied inside this square root function. And so we'll look at the examples for that. So the example of P chart, let's say that we are mass producing product, and the operator at various intervals takes 50 of these units and inspect them to see how many are good or bad. And we have 15 samples. We have got 15 times we've gone to the production line, picked up 50 units and checked them out. The first one, there were 10 of them defective. The second one also had the 10 of the 50 defective. Well, the third one had 9, the fifth one had 4, and so forth. So I've got 15 of them, and these are 10 out of the 50 being defective. So if I take the ratio of 10 over 50, so I've got the percent defective, right? It's 0.2, 0.2, 0.18, and so forth. So my P bar then is the average of this percent defective. That's 0.1507. To get the upper control limit and lower control limit for the chart, we go back to the formula of P bar plus and minus 3 times this square root of P times 1 minus P, over n. And so if you substitute 0.15 inside over here, plus and minus 0.15 times 1 minus 0.15 divided by 50, you get an upper and lower control limit for the P chart. And then we can plot the control chart. So here we've got from that calculation, I've got my upper control limit, I've got my lower control limit, and then I'm plotting the percent defective on the mean value and checking it. Obviously, the process is in control as we're not out of control, but there are issues whether or not these so many samples are below and so many samples are above, as opposed to be randomly distributed. So that's a notion of P chart. And one thing I need to emphasize that because these control charts are representing a physical process, the control limit, when you do the calculation, you may end up with lower control limit to be negative. At some, the calculation doesn't recognize that it's a physical process, but we know that the physical process, a negative control limit does not mean anything. It does have no physical meaning. And so whenever you have a lower control limit that's negative, you automatically put at 0. You don't go below 0 because it doesn't make sense. We'll just leave it at 0. Now in this case it was 0, so there's no problem. But if it was negative, and we see some examples of that, we're going to reset that to 0. Now, for the same process, because we were doing 50 samples each time, 50 units each time, so I can use an NP chart, which says that I can, instead of using that ratio, I can take the actual number of units that were defective instead of taking that ratio, so 10, which is really multiplying the P average by the sample of by the unit in my formula. So I'm calculating the upper control limit and lower control limit based on multiplying that 50 by that average, and then the same thing for the standard deviation. If you multiply by n, that ratio of 1 over n will disappear in the parentheses, and you get this in this formula. So I've got upper control limit, which is essentially what I had before for the P chart. It just multiplied by 50. And you can plot it. So instead of having a 0.2, what's a 0.3 or something as upper control limit, now I've got 15 here as upper control limit and lower control limit. It may just look a little bit better. It doesn't really make any difference in terms of interpretation of the chart. Okay, so that's for P and NP when we are measuring number of defectives per sample. Sometimes we're concerned in terms of how many defects are in the unit. So if we think about it, when a car comes off the production line, we just don't throw it away if you see just a scratch on it. So in the attribute chart, we're starting to look into how many defects are on the unit, and then try to address those and see whether or not the process as a whole is producing. So we use C and U chart for the attributes when we're measuring the number of defects per unit. So if the formula for the C chart is again very similar to what we had for the other P chart, it's C bar plus or minus 3 square root of C bar, which represents the 3 standard deviation. So that's for C bar. If we are using the U chart, then it's very similar, but it's a little bit different. And the difference between C and U is that in the C, the units are identical. So you're counting, let's say that we're just producing the same automobile off the production line. So the cars that are coming out, they're all the same. And we're counting the number of scratches and the number of defects and problems, missing bolt or whatever, on the units. On the other hand, if you're producing things that are different sizes, then you're using U chart. Now, one good example of that I'm showing is that maybe you're producing software modules. Well, the modules are of different size. One of them could be 10,000 lines, the other one could be 15,000 lines, 20,000 lines, and we're looking at the number of errors per 1,000 lines of code. Then we're using a U chart. It could be similar to when you're producing sheets of paper or sheets of glass of different sizes, then when you're counting the number of defects, because the sizes are different, while the number of defects would be different in a sense. And so how do we address that in a standard way? That's how to using the U chart. So for the C chart example, I said cars, so let me say that we're taking cars off the production line once in a while, taking one as a sample and counting how many defects are on that car. So the first one had 14, the next time we sample it was 13, and so forth. So out of the 10 samples that we checked, there were a total of 170 defects on those 10 cars. So try to get in the control limits for this. Here are my defects from this horizontal table to the vertical one. And I'm adding all the defects together, the 170 divided by 10, that means the C bar is 17, and that's my average. I'm putting it in this column. So what's my upper control limit? Upper control limit is C bar plus 3 square root of the C bar. So that would be 17 plus 3 times square root of 17. And that's 29.36. So I'll put that in this column. And my lower control limit is C bar minus 3 square root of C bar. And that's 4.64. I'm putting it in this column. And now I can kind of highlight this, go to the insert on an Excel sheet and plot my control chart. So here's the control chart for that C bar. The average was 17. You can see that red line, and the upper control limit 29 something, and the lower control limit was 4 and something, and so I'm plotting the number of defects per unit of sample. And I looked at it and look at this and say, well, the process is a control. It looks like those things are randomly distributed, so well, this process is stable and in control. This is what I expected. Now, the point about the control chart and whether the process is in control versus the process being capable is that this process is in control, but it may not be capable. In other words, some of these units, if your customer does not accept a unit with 14 scratches on it, then your process is not capable, although it is in control, because the inherent variability of the process shows that that variation is randomly distributed out the mean value. But if the customer says, I'm not going to take any car that has more than 5 scratches on it, then you're going to have a number of these units that are not going to be acceptable. That's a difference between process capability and control limits, or the difference between the specification limit and control limits. So we showed that the C chart. Now in a U chart, I talked about the software module. So let's say that we have 24 software modules that we have produced, and this one was 6,000 lines for the 300 lines of code, whatever these are the lines of code that we have in each of those modules. And then as we've tested them, we found out that this unit had 13 defects or errors in 12, 7, and so I've got the data from past experience on these modules that how many defective lines we had in the module. Now to handle the U chart, I need to standardize my size. So I'm going to pick 1,000 lines of code as being a unit for this production. So the first module then consists of 6 units. The second module consists of 4.3 units, and so forth. So I'm going to divide. I could have picked up 2,000 lines, go to 500. You're going to need to decide what the sensible unit will be to standardize, and then you standardize how many units is in each of those samples. And then I'm going to take the ratio of the defectives, right? So I've got 13 defects. I want to know how many per unit. So I've got 6 units in here. So if I divide 13 by 6, I get 2.16. So I'm going to take this column and divide it by this column, and I'm getting the defect rate per unit. And at the bottom, I've kind of averaged the size of the module and the number of units, and so the average number of units, the total is 92.3 divided by 24. I'm getting the average to be 3.25 is the average of the rates here. And the sample size, because these are the number of units, if I take the 92.3 and divide it by 24, I'm going to get 3.84, which is my n bar, the average of unit size. So what's the formula for upper and lower control limit for U bar is, for the U chart, is U bar plus 3 square root of U bar over n, which in this case we'll use the average of n. So we can now plot that. That's the mean value of the rate, and I've got the observation of each of the rates from the samples, and I've got the upper control limit and lower control limit, and so you can see that this process is not in control and certainly not neither also stable. So we've got a problem in our software development. The other example is that that was when I can average the unit size and use that to calculate the upper and control limits as a standard line. Now we could also use each of these sizes individually. So you could see the difference in the formula is that I'm using the U bar plus and minus 3, the square root of U bar divided by Ni, and Ni represent each own number of units per sample. So in this case, if I taking the U bar, which is 3.52, and then the N bar was the average in here, but the upper control limit then is the center line plus 3 times the square root of the average divided by its own n, which in this case will be 6, 4.3, and so forth. So I'm getting upper control limit and lower control limit. This is not based on the average of unit size, but based on each unit size of the data point. And so you get a jagged upper and lower control limits. So if that's what I calculate here. If I plot this, the difference is that if I were using the average N bar, which is average of unit, I got that a straight line for the upper and lower control limit. The plot of the data points is the same. But if I'm using each own, in each sample, I'm using each own units in the square root, then I'm going to get these upper and lower control limits, which is a little bit different. And both of these charts are generally used depending on how you want to represent your data. And I've put them together here, example 1 and 2. So in this one is the previous one where the upper and lower control limit are constant. This one, the upper and lower control limit varies by the number of units in each sample. And so again, it's still these points are out of control there, and it's also out of control here. So that covers the attribute chart and the process capability, as well as the variable control chart that we covered in chapter 1 and chapter 11 and chapter 12. Now let me talk about Six Sigma. Six Sigma is covered in chapter 13, but really hasn't been covered that effectively. And so I like to cover it more detail here for both understanding and application. Now what is Six Sigma? Six Sigma, when we talk about Six Sigma, we're talking about standard deviation of a process. So 6 sigma means, physically, it means 6 standard deviation. That's the statistical value of the 6 sigma. But it's also a measure of quality, and we're showing what it means in terms of the 6 sigma variation, but your specification is still kind of different from process variation. It's also used as a methodology for process and quality improvement. And so when companies talk about their Six Sigma program, they're talking about effort to reduce variation of their processes by using problem-solving methodology to reduce those variation and get more closer to Six Sigma. And so in that context, it could be incorporated into a total quality management program with kind of a business management system plus a Six Sigma program could be equal to a total quality management. And so companies like GE had a company-wide initiative to generate breakthrough in a number of different processes. So there are different. The point I'm making is that when you talk about Six Sigma, depending on who you talk to, there are different definitions of what Six Sigma is, and this is a part of that set of understanding of the Six Sigma. But why Six Sigma is important? The issue is that if you look at various processes and you say, well, 95%, I mean, in the old days, actually cars coming off the production line, if they were 97% good, that was great. The factory manager or production manager will get a bonus. But when you look at the 99% being good and only 1% producing bad product, in different contexts, is really not that good. So if post office was operating at 99% good, that translates to 20,000 lost mails per hour in that operation. Or if you were thinking about your drinking water be 99% good, you'll be drinking 15 minutes of unsafe water per day. There's 5,000 incorrect surgeries per week if the hospital were operating at 99%. So for a large process, 99% is not that good. And each time you have got a percent defective, means that somebody's getting bad product or bad output. So as the customers became more demanding better quality and companies competed with each other, then there was push for better quality and better output and not having any defect. Excuse me. So the Six Sigma goal, when we talk about it, is really eliminating defects from the process. And by definition, any defect is actually takes away from the profitability of the company, because either you have to fix it or you have to throw that product out. And so each time that happens, then you're losing money. So the idea of improving processes so that the outputs always be acceptable to the point where only 3.4 defective output is produced per millions of output. That's what is defined as being a Six Sigma. So in a process that is, if you kind of put a sigma value on the process and say this process is a 2 sigma process, that means that out of 1 million output of that process, that 308,537 of the units that are coming out are not acceptable. That corresponds to only 69% of them be good output. If the process is a 3 sigma, then it means that more output is acceptable, so that's reduced to 66,000. If the process is 4 sigma, that's 99.4% good. And if the process is 6 sigma, then the output effective is only 3.4, which means 9 fives here, 99.999% of the outputs are good. That's a definition of a Six Sigma process. Well, not all processes are Sigma. There are some processes that are Six Sigma. A lot of processes could be at 3 Sigma or 3.5 Sigma. And companies who have programs for Six Sigma, they're moving their processes from wherever they are, which is normally a good company, could be around 3.5, toward the Six Sigma. And if it requires to get to Six Sigma, then they can make an effort to get to that. But sometimes the economics may just show that 4 or 5 is good enough in terms of the cost-benefit ratio or acceptance. So with that understanding of 3.4 per million is considered to be a Six Sigma process. So what does that physically mean? Now, first of all, let me just point out that when Motorola came out with the idea of 3.4 defects per million to be a Six Sigma, some of the statisticians look at that and said, went to Motorola and said, well, where did you guys go to school? Because we cannot calculate the process that you call 3.4 parts per million being defective as being a 6 standard deviation in control. Well, Motorola people said that, yeah, that we understand that, but in manufacturing, where you, as a statistician, may not have a good idea, the mean of the process tend to drift if you're having machineries and production line. It drifts up and down, so it's not always on the design mean value. And so we have made a 1.5 tolerance for the mean variation. So we're giving that as a tolerance for the mean, and so the 6 sigma then is actually 4.5 sigma on each side of that tolerance. So if you just add 1.5 to the 4.5, then you get 6 sigma. That's how that is how it's being defined. So a 6 sigma 3.4 is not statistically true a 6 sigma, but it is a 4.5 sigma, and that resolved the paradox of how did they come up with 3.4. So as a quality measure, so that's when we talk about a standard deviation 6 sigma being 6 is standard deviation. But a process that's a 2 sigma means that there are a number of points that are outside the target value. The target value is at a specification limit. So in this case, if a process is a 2 sigma, means that 308,000 of these darts that we're throwing is going to be outside the bullseye. If a process is a 6 sigma, then you can see that all of them are clustered in there. But if I throw 1,000,000 darts to this board, there are 3.4 of them could fall outside the target area. That's the difference between a 2 sigma process and a 6 sigma process. If you look at it differently, so I'm going to having a process that shows there is a variation here when we talk about process capability. So we've got a process that has this mean value and has a variation around that. If my specification limit is tight, around 2 standard deviation, then it means that these black areas of the output, up or down this process, is going to be unacceptable. They're going to be defective outputs. So this 2 sigma process, the standard deviation, 2 standard deviation correspond to the upper specification limit, and the minus 2 standard deviation is lower specification limit. And so I've got a number of outputs that are going to be unacceptable. In a 6 sigma process, if you think now I have this process and I kind of grab the 2 sides of it and squish it so that the standard deviation is reduced significantly, going to show like this. So I'm still having my specifications limit the same as I had before, but now the process is so tight in terms of variation around the mean that everything that we are producing is within the acceptable tolerance. And that is the definition of a 6 sigma process. That is so tight around the mean value that only 3.4% of the output are going to fall outside the limit. Now, you can get to a 6 sigma in 2 ways. You can, in this case, if I can negotiate with my customers so that I can push these limits all the way to here and to here, well, suddenly this 2 sigma process is going to be a 6 sigma process without changing the process. Now, that's kind of a wishful thinking, because if you're designing products, you can't, increase the tolerances that the physics kind of dictates. Or if you have a customer that has specific demands, trying to tell them to take more defective products is probably not going to work. So the notion of the 6 sigma is that we're going to stay with the specification limit, but we're going to improve the process so the variation is reduced so much that all the outputs are going to fall within the limits. Now, in a true, I talk about a 4.5 sigma and 1.5 for tolerance for the drift of the mean. If the process was a true 6 sigma, you will see that the 6 sigma on this side of the mean, 6 sigma on the other side of the mean for the process, there is the amount of unacceptable output is 0.001 parts per million, not 3.4, but 0.001 and this side 0.001 on that side. So a true 6 sigma process is significantly more tight than what is defined as a standard Six Sigma process. So on that notion, if we don't allow off-centering for the mean value, that 1.5 that I talked about, if there was no off-centering, then a Six Sigma process can only produce 0.002 defects per million. A 3 Sigma process will produce only 2,700 defects per million. Now you start, if you allow different tolerances for the mean, 0.5, then you could see that the defect rate for the Six Sigma goes a little bit higher. 1 you go to 0.39, and when you get to 1.5 you get 3.4. Now this was purely the decision by Motorola to pick 1.5, and that became the standard of the industry. They could have picked up 1, they could have picked up 2, they could have picked up 0.5, but probably from their engineering experience they decided that 1.5 was a good measure, and then it became the standard. So it is a standard, it's defined as 1.5 tolerance, and so 3.4 is represented as Six Sigma, while it's not a true Six Sigma. And to show that, okay, so let's now look at an example of how do we calculate the Sigma performance of a process. Now, there's a notion that Six Sigma is all for manufacturing. It's really not. It's a measure of how bad or good our process is for producing an output. So I'm going to illustrate this with a different type of process, a billing process, something that every organization is dealing with, right? So it's not manufacturing. It could be your organization. So we're looking at the billing error. You take a sample of the bills that went out and count how many of them were defective. And in this case, we look at 1,000 bills, and 150 of them had problems, some sort of a problem. So I got 150 defects per 1,000 bills. So how many of them were good? 850 of them were good out of 1,000, had no defects. So if I take the 850 divided by 1,000, I get 0.85 non-defective rate. So what is the Sigma rating for this process? To get the Sigma rating, I need to find the z-value for 0.85 and then add the 1.5, that tolerance, to it. Now, how do we get this? Let me go to a normal table, and we have this in the resources. You could use a normal table in the book, but this is more detailed than here. So the z-value that we talked about in the first module, that the cells of this table represent the probability. That's the percent not defective, right? I had 0.85. So if I look through this table to find my value, well, it's somewhere between these two. I got 848495, got 85083. So let me just take roughly this, or I can interpolate between these two. Now, what is the z corresponding? The z value for this is 1.03 or 1.04 or somewhere in between. Okay, so if I go back, you see that I interpolated and I got 1.036. That corresponds, the z value is corresponding to the x-axis of a unit normal distribution, and then I'm going to add the 1.5, which is my tolerance to it. So this process is a 2.5 Sigma process. Okay, so now you can calculate your Sigma performance of any process that you have. You can do it for your own. Take whatever you're producing, take a sample of that, estimate, even if you don't have physical data, and do an estimate of what the percentage of the time you're doing perfect output, and what percentage of the time your output, whether it's a paper or a product or software or whatever it is, that has some kind of a problem. You can roughly or actually get your percentage non-defective. Go to the table, look at the z-value at 1.5 to it, and you know at what level you're performing. The beauty of this Sigma calculation is that you can calculate, you can compare any process to any process. there is no apple and oranges when we're talking about the Sigma performance. And so you could compare the performance of your billing process, the performance of your software development. Of course, these are different type of processes, but in terms of the Sigma performance, the numbers are these indices can be compared. So back in many years ago, Motorola actually calculated the defect rates of or sigma values for different type of processes. So, one of those things is the IRS tax advice. So when you get to close to the April 15, a lot of people call IRS to find out, ask for advice on different issues, and they get an answer on the phone or however they're getting it. Well, they calculate that those answers are not always correct. And so there are defects in terms of the answer they provide. And at that point, the IRS was actually performing around 2.2 or 3. I believe a year or so ago, I saw somewhere where the new data from IRS was representing somewhere around a 3 sigma process, which has kind of significantly improved compared to 20 years ago. Restaurant bill, they looked at it and they found that was around 3.2. Good companies in U.S. operating around 3.5 if the company doesn't have an improvement program. Now, if you have a Six Sigma program, then this could have moved further up. But a good company that doesn't have initiative on Six Sigma or process improvement could be around 3 to 3.5. Prescription writing, the doctor's writing, they ended up being 3.5 when it goes to the pharmacy trying to read and whether or not there has error in them. Airline baggage handling, around 0.4. But the airline themselves, before considering terrorism, were over 6 Sigma. In other words, when the plane takes off and from East Coast to go to West Coast, we don't want that to stall in mid-air. So that engine produced by GE, other parts of the plane, they're performing better than 6 Sigma. But the airline don't care that much about the baggage handling. Well, what happens is that if they lose your luggage, well, they give you $100 to buy another one. And so they figured out that it's cheaper, and since all of them do the same thing, there's no competition to, just dump the luggage on this, the luggage claim area, and some people lose their luggage, and you may have your own personal experience with that, and you're out of luck. That's why, if you're traveling, or when I'm traveling, with the most important paperwork, you don't put in your luggage. You carry all of that with you. So because you can't trust that it's going to be there if you're making a presentation in another city, and you land and your luggage isn't there. What class companies could get into 4.5 Sigma when they have initiatives around 6 Sigma? So now 6 Sigma program, which people refer to in many companies, could be a company-wide initiative or particular focus on some breakthroughs, you can consider as a strategy both because reducing defects always improves the bottom line. Plus, it increases customer satisfaction. It gives you better press, in terms of the quality of your product and so forth. So it's a good thing to do, but nothing is for free. So initiating a Six Sigma program and going through it, you're going to have some costs associated with it, with the company whether willing to make that investment or not. So going back to the history of the Six Sigma, back in 1981, and at that time I was at the lab, and we kind of following Motorola. They had a 10 in 5 initiative. Bob Gallen, the CEO of Motorola, challenged the company to improve the reliability of his pager by a factor of 10 over 5 years. Now, so the people went to work and they tried to improve the processes, and they came back and to in 1987 to the CEO meeting and said, okay, Bob, we've got it. Now we have improved that and showed the data that they had, that the reliability was tenfold better than it was back in 1981. So Bob Galvin kind of got carried away a little bit and said, okay, now I want perfection. I don't want any defect. Why should we even have this level of defect? So it says, well, the people sitting in the room, they said, well, look at each other and said, okay, Bob, we need to think about this. We'll get back to you. And that's how that meeting ended up. And so they went out and said, okay, what are we going to do? What does it mean to be perfect? And Bill Smith, who was an engineer at the time at Motorola, he came back with this idea of 3.4 defects part per million and called it Six Sigma. And as I showed it before, what does it mean in terms of variation of the process versus defect? And so they went back to Bob and said, okay, here's our target. We're going to push for 3.4 defects per million, and using the Six Sigma process. That's how the Six Sigma process started back in 1987. And in 1988, actually, Motorola was doing pretty well. And so they won the Baldrige Award, one of the first companies that win the Baldrige Award. And they have been using the Six Sigma in the company for years. But it didn't really catch up with other companies as much. And so it was, for many years, it was just kind of in the back burner. Some companies started to look at that, in particular Allied Signal, which is now part of Honeywell. The Allied Bossidy, Larry Bossidy, was the CEO of Allied Signal. He used Six Sigma in his company and was claiming that he saved significant amount of dollars because of that reduction in defect. At 1.2, maybe he was playing golf with Jack Welch, the CEO of GE, and said, hey, Jack, you really should look into this. There's money to be made. And so Jack Welch went and started looking into the Six Sigma, and he became really a staunch supporter of Six Sigma and launched his own program in GE. And as he saw the value coming out from the program, he went around and talked to other CEOs, and so he was really the one that gave the Six Sigma program significant prominence among the large companies. And today, many companies are using that for improvement in particular areas. So that's a little bit about the history of Six Sigma. But looking at the GE itself, at the time, their processes in, looking, this is 95, 96, just like any good company, they were averaging around 3.5 Sigma, which means 35,000 defects per million. Now GE is a big company, and I pointed out earlier, they make jet engines, which is better than Six Sigma, but they also have refrigerator, toasters, microwave oven, and you think about millions of those refrigerators going out to customers, and 35,000 of them has warranty calls. Well, that's a lot of money the company loses. And so that's how they got behind the Six Sigma, saying that, well, if we can reduce that, going from 3.5 to 4 or 5, we can significantly reduce defect. First of all, our customers are going to be better and happier, but we're also not going to have to, send out that many warranty calls out and fixing the problem when we ship this product out. So based on that experience, now this is in 1996, Jack was saying that this is the most important initiative this company has ever undertaken. It will fundamentally change our company forever in terms of looking at processes and improvement. Now that's how he believed it, and I'm just using that as a cliche here, but a lot of other companies have seen the value. Now GE took what was essentially the standard, we call it problem-solving methodology, or Deming process, or Deming chain, or Deming improvement cycle of measure, analyze, improve, and control. And they added a define to it, and they came out with this 5-step process, which is now DMAIC, as being again a standard approach in Six Sigma programs to define your problem, measure it, analyze it, improve it, and control it. That's a problem solving. But if you're using then tools and techniques of Six Sigma and other quality measure within that to move your process variation toward that 3.4 per million, then you are working in a Six Sigma program. So that's the a step definition of each of the steps. And part of that defined process was that we don't want to just initiate a quality improvement on anything that goes on or anybody that asks for it. So let's kind of understand, is that a real problem? Is that an important problem? Is that impacting our customer? And so you're going to need to do some initial homework to scope the problem in the sense that it is of value for the organization to put a team on it, to do all this effort to make an improvement. And so with that initial work, then you have to now go further. Once you have a team in place, then you can go further, collect more data, then do the analysis of data, find out the root causes of the defects or variation in the process, and come up with the improvements. And then if you achieve that improvement, then try to control it going forward. So it's a scientific method in a sense, but we're putting or couching it in terms of a Six Sigma program. And I pointed out earlier, companies that have Six Sigma program doesn't mean that every process is a Six Sigma process. You will start with a 3.5 or 3 or maybe even lower than that. And when you start making improvement to your process, your Sigma performance goes up. And GE experience, they found out that it probably was very easy with tweaking some stuff to go from a 3 to 3.5 to 4 and then making some improvement to get to a 5. But trying to go from 5 to 6 required a significant amount of rethinking of the process. And so that's the design for Six Sigma came out, is that it sounded like cutting through a barrier, sound barrier to get to that effort. So this is considered to be a significant effort because you're going to need to go back and rethink the whole design process and figuring out how can I design this product to be defect free versus here you've got an existing process and you're trying to tweak and improve it. And so in most cases companies will end up somewhere between 4 and 5 and not try to go to that. But if the process requires that you get to the Six Sigma, because people's lives are dependent on it, we're talking about the jet engine or the shuttle software or some other things that medical products that people's life is dependent on it, then it probably worth to go further from 5 Six Sigma to Six Sigma, and the companies make that effort. But it requires significant additional effort, we call it design for Six Sigma, and not improve to Six Sigma. It's very hard to get from an existing process to a Six Sigma, keeping the existing process as opposed to going back to the drawing board and redo the process from the start. So now I've talked about the Six Sigma and the GE and all that effort by Jack Welch. Now let's look at the financial data that GE experienced. In GE, all projects that are proposed for Six Sigma are rigorously that initial evaluated for or not is important. And they set at least a goal that in a project expected to have at least 175K of financial impact before they assign it to a team or a black belt to do. And so when we talk about the belts, and GE has these black belts, and other companies have, these are highly qualified, highly experienced, and with statistical as well as Six Sigma and engineering background, to be kind of being a consultant to the organization, going around as freelancers and pick up projects and work on making improvement. But it wasn't just a free, for whatever you want to do. In GE, they had a target of at least producing $1 million financial impact per year. So I mean, that was the target, to pick up projects, work on it, make improvements, and show that they have at least achieved $1 million per year. I mean, you look at the cost-benefit analysis of that. A highly valued engineer or black belt at a company like GE probably get like a $250,000 in salary, and when you add the benefits and others to it, it could be costing the company about $500 a year. So if he or she produces $1 million of savings, then that's not a bad return. And so that's how they did that. And looking at the financial impact, when GE started this program back in 1996, as I said, there is nothing for free. So he has to train people, has to create teams, to let them go around and work on this project. So the first year, if you look at these columns, the red column is that it cost him $200 million in that large company to initiate and run this program. The saving in that year was only 170. And so if you look at the short-term return, that year there was a $30 million cost that didn't get recovered. But you go to 1997 as program went on, and we're talking about quality improvement really pays off in the long term. Then you still have to maintain those programs, pay those consultants, and time for the teams to work. And so there was a $380 million investment, but the return, the return was 700 savings, which means that there was a $320 million net benefit from the program. And this is the last year that actually presented the data. They saved $1.4 billion from the program. Now, this is not the data that people just created it. When Jack Welch started this program, he called his CFO and said, when the people come back and telling me that we've saved money, I want you to sign off on it. It has to be real hard dollar saving. It's not something wishy-washy. And so this data are pretty hard data from that company that they published. And then, Jack Welch was showing it to other CEOs and other conferences, and so kind of getting people behind the program. Now I'm going to show you that a different example. I showed you how to calculate the Six Sigma for a billing process, but let me also show you for an HR process. All companies, when they have problems, employee get injured on the site, they have to report it to OSHA. So at the end of the year, a company had to report how many injuries they had. And there are some definition of what is a reportable injury. But in this is a Motorola plant down in South Florida, so it's an actual case study. And in that year, the person that was analyzing, they look at the Sigma performance of the injuries on the job. So that year, they were the plant had 1,386 employees. And when you look at employees on the plant, well, 113 of them got injured during that year on the job. So these were reported to OSHA as 113 injuries. And so you can think about it, any employee that walking around the plant during the year has an opportunity to, every day has an opportunity to get injured. So to calculate the defect rate, here we have the total number of injuries, 113. The total number of units are the people walking around the plant or doing work, so 1,386. So the defect rate per employee is 0.02 per year from that data set. To calculate the defects per million, the part per million, then we'll take that defect rate. Now, how many days are in a year? The working days are about 250. So the opportunities for people getting injured is really every day, every person has that opportunity to get injured. So what we need to do is scale it up to 1 million. So we take that defect rate, which was based on 250 days, and if you scale it to 1 million days, multiply by 1 million divided by 250, you get the part per million of being 3.26. Now this corresponds to a sigma level of 4.91. Now I showed in the billing process how to calculate the sigma performance. So I'm going to show that in here how the 4.91 you can get that. The non-defective rate, the defective rate was 0.082, right? divided by 250, which was the number of days the person could be subject to potential injury. If I take 1 minus that rate, I get the non-defective rate per day per person as 0.999673. And you go to the normal table and get the z-value for that and add 1.5 to it, you get 4.91. So there are two ways to get the sigma. If you get the parts per million, you can go to a table, and I'll show that shortly. Or if you get the percentage defective and percentage non-defective rate, you can use the z-value and add 1.5 to it. So the second part of that case study was to, beside the fact that somebody get injured on the side and they have to be reported, and it's really not good for the person, it's not good for the company. So it was an initiative to reduce these kind of injuries. But at the same time, each time somebody gets injured on the job, while there's a loss of revenue to the company, because beside the fact that it has to go to the doctor and get paid for all of that, there's going to be a number of days, either one day or multiple days, that the person, would not going to be at work, and so those are productive days that are lost. So this manager also look at the work they lost, which is the potential financial loss to the company. So the opportunity for error in one unit is per work day that are lost out of the 250 days. So let me look at the data here as this person calculated. So the sample calculation, the unit was 346,500 work days per year. Now what it means is that remember we had 1386 number of employees. Each of them worked for 250 days or potentially could work for 250 days. And so the total number of days that are at risk of getting potentially lost is this multiplication of these two, which is this number of days. Now when they look at the end of the year of how many days per person were not at work because of those injuries, they found out that the total number of days was 3,218. So it's hard to keep track of these type of data. So they had 3,218 days of work they lost, and potentially there were this many days of work, right? So you divide them together and you get the defect per unit. And now if I scale that to a million, multiply by a million, I'm getting 9,287 parts per million in terms of the work they lost in that plant. And that corresponds to 3.85 sigma. So it's not the same sigma because of the different data set or different values. Now, how do I get to do that from the table? You could actually do the same thing as I did for using the z-value to calculate that, or I'm going to show you a table here. So my defect part per million is 9,287. There are tables, and there are on internet. There are also calculators to give you that. But this table, what it does is that you have got the part per million, and then you've got the sigma performance level. So this is essentially using that z calculation that I had and putting it into a table of sigma value. So I had a 3,000. Let me go back and what was the number again? There was the total of 9,287 parts per million. So I'm going to come into the parts per million to 9,237, and you could see here that the corresponding sigma is 2. Well, that's 9,287. 9,287 is somewhere in here as 2.91. And that says 3.86 sigma. That there seems to be an error in here. That is not actually the number it should have been. I need to go back and fix that. But the way you do it is to go to the table, You can do both ways. If you have a sigma preference, somebody tells you what your sigma level is, you can go back and look at the table and say, oh, it is here actually. Between nine, I was looking at the 90,000. I'm sorry, it's 9,327 is somewhere in here, and so the sigma performance was in that range. So if you have performance level, you can look at how many defects you're producing. If you have the parts per million, you can look at your sigma performance. Sorry about that. And so in that plan, they actually tracked the cost of injuries. So you got three plots here starting back in 1990 when this program initiated, and then they initiated improvement activities under the Six Sigma program to reduce these kind of injuries and the cost of the work they lost. And so you see three graphs in here. The blue one is the direct cost. The direct cost is that if somebody gets injured, need to go to hospital, you got doctor bill, all that, then paid for out of pocket by the company. That's the blue line here. The green line are the indirect costs. That's the salary that person get paid even though not at work. So these are the indirect costs that the company incurs, but we're not getting any revenue for that. And the total was the red. And so when they started working on the program, then from here, which was almost $10 million at one point, coming down all the way to somewhere around $1 million, factor of 10 improvement over a number of years. So what we covered here is these two modules. I covered the descriptive statistics, some of the fundamentals of a statistic. Then we got into I covered the quality tools, some of the quality tools, Pareto chart, run chart, histogram. Then we got into the application of control chart, and then for both for variables and for attributes, I covered the process capability, and then spent on essentially covering what the Six Sigma is and how you calculate the performance of any process. It's really not as complicated as it sounds, as I showed you in both of these type of examples. So this concludes the this module. I hope that you kind of helped you with the learning in the course. And if there's questions, always welcome to send me an email.